Hello, everyone. My name is Mark Ashton-Hust. I'm one of your TAs for this semester, and I'm working through problem session 3 today. We're going over 4 of the problems in your homework, all consisting of diode applications. The first being 4.4. There's a lot of steps in there, A through K, so I'm not going to be doing all of those. I'll probably just be, I think I'll just be doing about 5 or 4 of them. Just you can do some on your own, but also if you need to come back to check, I should have done enough where you can use some of my help. The second one will be on question 8, 4.8. That's diodes using Thevenin's theorem from circuits 1. Should have gone over. Question 28, 4.28, which is also diodes and solving for currents, voltages around there. And then lastly, 29. So we begin with the first one, 4.4. I have an iPad here where I'll be drawing the questions using this kind of as a whiteboard. I'll begin 4.4, and I'll start with A. So we're going to start with A here. And A starts, we have a voltage input here, and we have a diode looking like that. We have a 1 kilo ohm resistor here. And our V out like that. So that is going to be our A, or question A. So second. So given per instructions here, we're going to have one thing I want to add in here. Sorry. So I'll name this D1. And I want to add that we have, let's make sure we know how to label our diodes. So we have, let's put a diode here, and then we have the wire coming out. This is going to be our anode here on the positive, and in our cathode here on the negative end. So we'll remember that, and I'll be using that terminology when I'm talking about this. So we have anode and then cathode. And this is important to know and understand because that's how we're going to know the bias of the diode, which if we're in reverse or forward bias. So we have a peak sine wave of 5 volts. So 5 at the top, so it would be 10 peak to peak if you're going the whole thing. And then the sine wave here is applied at the input. So we have a 5-volt sine wave input, and it's at 1 kilohertz, which will come into, which will be important when we graph things out. So looking at this, we have the peak sine wave voltage of 5 volts. So when we have that wave going out, let's say this is 5, this is negative 5 volts. We're going up, down, up. This is 1 period, so that'll be 1 kilohertz. And then up, down, up, well, sorry. Up, down, up. And then this would be 2 kilohertz, 2 periods. So that sine wave has a positive conducting cycle here, and then negative. So it'll be negative for half and positive for half, which means that this V input is going to be going between a max of 5 volts and a minimum of negative 5. Therefore, we're going to set this up in 2 ways. So we have our positive half of the cycle, and the negative. I'll start with positive. So then we want to define what's happening in that positive half of that cycle. Well, in that positive half of that cycle, it'll be positive. So this diode D, and it's being applied to the anode, right? So we're having the positive voltage on the anode. That means the diode's going to conduct. So it'll be conducting, which means it's going to act as a short. It'll allow current to pass. And this would be considered what's called forward bias. Ideally, and we're working with ideal circumstances here, it might change. It's usually what it'll change to is about 0.7 volts, but ideally the diode D1 is going to be equal to 0 volts. So the 5 is greater than that 0, and that's why it's going to conduct. So then if we go to the negative half of the cycle, I'll zoom out here. That diode now, that negative is going to be less than the 0 volts we have at D1. Therefore, it won't be conducting, so not conducting. It'll be an open circuit, which open circuit, no current. And then that's what's going to be called reverse bias for that diode. So this one is going to be probably one of the one of the most simple ones. The only thing you'll have to think about is what if this diode was switched into this, and I believe that's question B, so I'll leave that for you to figure out. And then we want to draw that out. So remember I showed you that first graph. So here I'm going to just draw out 5 to 5. So we have our axes correct. So we have positive 5 volts and then negative 5 volts here on the bottom. We have 0 volts here. And then let's make this T1, T2. We'll define these. And T3. T4 would be 2 whole periods. But really seeing the T1 to 2 is important. So when doing this, 0 to T1 might be, so 0 to T1 will be conducting because it's sine waves. So 0 to T1 is going to be that positive sign, positive that voltage. We can define, so what I'll say is T2 is going to be a full period there. So we're running at 1 kilohertz. So 1 kilohertz is 1 kilo and then inverse seconds of the kilohertz. So 1 over 1,000, which would be 0.001 seconds, is going to be T2. So that means T1 is going to be 0.00005 seconds. And then I'll define that here. So we have T1 equals 0.00005 seconds. And then T2 equals 0.0001 seconds. My bad, that's wrong. So 0.005 seconds and then 0.001 seconds. There we go. Apologize. So then the positive half cycle is going to be 0 to T1. So that means we will conduct from 0 to T1, but we won't conduct from T1 to T2 because that's the negative half of the cycle here. And on that negative half of that cycle, T1 to T2, the diode won't allow that to conduct. There's going to be a short here. There's going to be an open here at D1. So then T2 to T3, when we start over again, is also going to conduct, but T3 to T4 won't, and this is going to continue on. Every positive half cycle, which will be the 0 to 1, 2 to 3, 4 to 5, will conduct. But the in-betweens, the 1 to 2, 3 to 4, where this VI is negative, we won't be conducting. So there I went over it. I went over that one a little more exact. So the next few, some of those things aren't going to change. Like T1 and T2 is not going to change, nor will that input. That 5-volt sine wave input at 1 kilohertz is going to stay the same. So as I go into the further problems, I'm not going to explain that as much anymore. But we will be doing new diode problems. So I'll move to the next one, and the next one I wanted to consider is C. So this one is the first one that considers what happens if we add 2 diodes in here. So we're gonna have VI again, we have our input, and then I'm gonna have diode D1 here, and then I'm gonna have diode D2 here, and we have diode D1, there we go, and D2. You see, they're facing opposite direction. This is going to be important. So D1 and D2, we have a resistor going down here to ground, and we have a 1 kilo ohm resistor, and then V out. Great. So I'll continue here, and then what I want to do is really we want to focus on that positive. We'll do positive half and then negative half. Think for a second what that might be. What's happened on this positive end? What's happened on the negative? So when the voltage is positive, we have, looking here, right, if you remember the diode I drew, we have that positive negative on the diode there, and positive negative. That means, or that positive half, this D1 is going to be open circuit. It's not going to be conducting. So technically, what it's really going to look like is we're going to have VI, and consider you're the electrons going there, and you're just going to hit an open circuit right here at D1. So we're done there. V out's not going to get anything. V out's tied to ground. So that's easy to write in here. So positive half, D1 is reverse biased. Now that I've named that convention, I'm going to leave it like that. Reverse bias means open circuit, non-conducting. So D1 is reverse bias, and then D2 doesn't even matter. It's not even a part of it because we're not voltage. D2 is not going to see anything. Negative half though, let's look at this. So D1 is going to perform the opposite. So D1 is going to be a short. It's just going to keep going. And then we get to D2. D2 is flipped from D1. So we're going to have the same exact problem as D1, where now D2 is going to be reverse biased. So D1 is forward bias, so it'll be a short, and it will conduct. But D2 is reversed bias, reverse bias. So what that means is that D2 here is going to be an open. So the same exact thing is going to happen. We have VI. We have here, we go through, let's say D1 is here, and it's a short. And then we hit D2. V out is all the way out here. And we got our resistor going down. So V out won't experience anything. So really what this graph's going to look like, and I'll go back to this, what this graph look like. copy this so we can use it. So I don't have to redraw that every time. So back here to C, 5 volts it's going to look exactly like this. It's just not going to conduct. There's no V out. V out should be here. There's going to be no V out, which means our peak forward voltage, so our VP plus is 0 volts, and our VP minus in the negative direction is 0 volts. And then, sorry, if we're going back to the first problem we had here, we have VP plus, I'll do these in color, VP plus equals 0 volts, and then VP minus is, that's 5 volts, and VP minus is 0 volts. This one is just 0 and 0. If we were drawing the whole line going through, we're just gonna go like that, 0. So now we can move here. Let's go to then another question. Let's do, so you can do D on your own. We'll skip to E. So E now is also going to have 2 diodes, but we're going to do something different. We're going to put these diodes in parallel. So we have E, and then we have our V in here. We have our diode with our cathode facing forward. D1. I'm going to do this. Go down here, we're going to flip that. And then this will be D2. And now while I'm drawing it out, we're doing the same process. We're trying to find the same thing. So start thinking about it for yourself. And also, if you're wondering too, maybe for the first one, we had 5 volts and 1K didn't do anything. 1K won't do anything because it's not, we don't have another, if we had another resistance here going through, yes, it would. And if you're trying to think what that would be, think for a second, that would be a voltage divider. But that other voltage, that other current source, resistance, my bad, the other resistance isn't there. So really the V out is just V in for peaks as of right now, that in that case. So we're going to do the same thing. We're going to do positive half. Think here, keep thinking, trying to figure out what's happening. So I'll write D1, D2, so we can, then we have negative. So on the positive half, think, so they're flipped. So that usually, since D1 and D2 are opposite, like kind of directions, that means really that they're going to perform oppositely. So if D1 conducts, then D2 is probably not going to conduct. So for that positive half of that cycle, D1 is it going to be conducting or is it not going to be conducting? You could think back to A. We also did this with B. We have that anode. We have the anode on the other side and then the cathode. Right, so is D1 going to be conducting or will it not? So D1 is going to be in so D1 is going to be reversed biased. So D1 will not be conducting. but D2 will be conducting. We can see that back when we look at A, right? D1 here was conducting. So D2 will conduct. So D2 is going to be forward biased. So that means, and thinking about that, are we going to get an output? Yes, we are going to get an output. We are going to get an output there because this is basically, so D1 becomes an open. So let's do this. And then D2 is just going to be a short. So we're going to go down, and then V up. Awesome. So we'll get all the voltage there. Awesome. Now let's do negative half. So on the negative half, it's, like I said, it's just going to be flipped. So D1 is now going to be forward biased. And D2 is going to be reverse biased. And this is going to be short V out. Awesome. So that means that it's going to conduct this circuit here. The original one is going to conduct for the whole thing, right? It's going to conduct for, it's going to conduct here for the positive half, and it's also going to conduct for the negative half, which means we're going to get something. T1 and T2 are still the same. We're still at 1 kilohertz. So we're going to get something that looks like this. Sometimes it's hard to draw. Sometimes there, I have to keep it going. So bad graph, bad look on that. Yeah, I knew the whole thing was gonna race. That's good as I'm gonna do. It's gonna conduct for all of it. So while looking at this, it changes nothing. We basically don't even need a diode there. Just put V in, connected a V out, that resistor. Awesome. Boom. So that was E. The next one I'll jump to, I'm going to do a big jump here because I think you've got enough information now that you could figure those out on your own. I'm going to jump to I. I'm going to work on I here. So working on I, we have VI, and then we have the resistor. That's 1 kilo ohm. And we have what I was talking about earlier. I was saying is we didn't have 2 resistors. Now we do. So I'm going to toss another resistor here. And also a diode with our anode, cathode. Name that D1. And ground, we have 1 kilo ohm. And then this goes out to V out. So this is what we have for I. So I is a little bit different, right? Because VI is here and it's not, we don't just go right anode. So a little bit different, but we're going to do the same exact process. We're going to do positive half and the negative half. So think for a second while I write that. So on the positive half, it's still going to be, we're still going to have like the voltage looking like that, right? Because we still got ground and then we're going to have the positive voltage of VI. So on that positive half, it'll be 5 volts max. The 5 here, it's going to be D1 is going to be in reversed bias. It's going to be a reverse bias. It would be the same thing as if we had VI and then like that. There would be a resistor here. So, and the positive half, there's not 2. D1, reverse bias. This means it's open, non-conducting, which means technically that 1 k ohm resistor there is dangling. So our V out, I will keep that. Our V out is going to equal our V in. That 1K resistor is just hanging off. On the negative half cycle, that's going to flip though. This is going to change because D1 is going to be forward biased. Because D1's forward biased, we have something new for our V out. Our V out is going to be a voltage divider. Reason for that, and we'll look at it, we'll have, say we had, this is our VI. Connect that to ground. And then we have our 1K here. And then we go down to 1K here. Well, now this is, the D1's a short to ground. So then we'll just have that to ground. So we have 1K, 1K, and then V out. And that's exactly what I was describing. So we have V out taken here. So it'll be a voltage divider over that 1 kilo ohm resistor. So when we're finding V out for that negative half, we're going to have V out equals V input, and then it would be 1K, 1 kilo ohm over 1 kilo ohm plus 1 kilo ohm. And that V input, because it's negative, the max will be negative 5 volts. So we'll have 1 negative 5 volts times 0.5. So our max negative voltage is going to be negative 2.5 volts. That's going to be our max reverse voltage. Up here. So then we can graph this, and then this is why I want to go over it, because this is going to be different now. Is we do have a positive half and a negative half. However, the negative half is not a full 5, it's half, it's 2.5, negative 2.5. So that means we're going to go up to 5 on this one, but we're going to come down to 2.5. Up to 5, down to 2.5. And I would write out 2.5 volts and then maybe a little dotted line there just to show. And then you could also do a 5 at the top just to show that it's not going to like 5.1. You could do that for all of them. So this one is interesting because this one's a little bit different because it changes that negative peak voltage you get. So well, the next one I wanted to go over is K. No problem, K. So we have K. K looks a lot different because we have what you're going to see here. We have a current source. We also have V out here, our current source there, which we set to or have as 1 milliamp. Then we have that. We have a 2 kilo ohm resistor. And then we have 2 diodes. We have D2, goes straight down. This is a configuration you might see in the future. This will probably come up again. It might actually come up again in one of our other homework problems. And then this goes straight to ground when they miss D2. And we have another one coming back out here, and we'll name this D1. Oh, that's a long one. We'll name this D1. And D1 is what's connected to V input. Remember, we got our negative, we got our positive, positive, negative, anode, anode, and then our cathode at the bottom. And then this one is D1. Labeling the diodes helps if you get a good understanding of what they look like and whether you're setting it up right or not. So, and we have that going. So then same thing. This diagram's a little bit larger, so we might have to use more than just half the page. So we have positive half and negative half, which are going to have the same. So for a positive half, let's look at D1. Actually, what I'll do here is make this easier. So positive half D1 is it forward biased or reverse biased? Let's look for a second. D1 is going to be in reverse bias, which means it is open and non-conducting. And then D2, though, right, we're going the opposite, so that goes there. This is going to be open. So there's going to be nothing coming from V input. But we do have this current source, that 1 milliamp current source, so that will matter. So we've just found out that the VI isn't going to have an influence on V out now, but this 1 milliamp will. And to figure that out, we would just use Ohm's law. And we know that Ohm's law is V equals IR. So in this case, we have the 2 kilo ohm, and we have the 1 milliamp of the 2K. So we have two of the three. We want to know the voltage, we have current and resistance. That's plugging it in. So for the positive half, our V out is going to be equal to 1 milliamp times 2 kilo ohms. Just 2 volts. Awesome. So now let's go to our negative half. Negative half, D1, look at it. If it was non-conducting, reverse biased when voltage was positive. So if it was VI is in its negative half, it will be conducting. So it will be forward bias. And then we need to find V out. D2 though, right? Look, D2 is going to go this way. When we're thinking about that way, D2 is going to be open. D2 is going to be reverse bias. So D2 is reverse bias. So what we have now is a VI. Let's make this easier to look at. Let's do this. So this is what we're looking at now. So we want to know the voltage across that 2 kilo ohm resistor, which would be 2 volts. But we also have a negative 5 volts that coming in right here. So the change we're going to have there is our V output is going to be negative 5 volts plus that 2 volts. So we have that positive 2 volts that's coming from up here, but we have our negative 5 volts coming down here. So that'll give us a total of negative 3. So our max positive, let me redraw D2 back in here. So our max positive, V peak positive is going to be 2 volts. And our V max negative is going to be negative 3 volts. I'm going to draw that again. Our graph. And then this, because this is from the source, that positive one is just going to sit DC at 2 volts. So it's going to look a little different. So from here, we're going to have that 2 volts, and then it's going to come down with a max of -3, which would be here. And that's what it'll be looking like. Which this one is a little different, and this is why I went over this one, because this one has a bit extra added into it. Now I'll go to 4.8. So look at that circuit there. And we're going to use Thevenin's theorem. So using Thevenin's theorem, we'll remember the first thing I want to find is going to be R Thevenin. And then R Thevenin, though, would do 3 things. So that means the load resistor is going to be an open circuit. We'll change that. The current source is going to be open, and voltage sources are going to be shorted. So looking back at 4.8, which I do not have that one actually written out. So I will grab that real quick. I have it right here. Anyways, we have the first part looking, we have this, we go down, we have 20 kilo ohms. And then we have a diode to here, and then we have V out. We have that here, and that's grounded. So what I'm gonna do is the diode will make, that'll be shorted. The 20K with, and this is using Thevenin's theorem, the 20K will be removed. We'll get rid of that. And then all voltage sources, current sources, we don't have those. So what we're left with here, and we're finding our Thevenin, that's what I'm going to start with, is going to be our 20K up at the top. And then we have this straight to VI, or V out, my bad. Or just in the V. And then we have 20K here. So what do we have here is we have 20K and 20K, and then what configuration are these 2 resistors in? We want the total, we want the resistance of the whole thing. So those 2 20K resistors to get our R Thevenin, they're in parallel. So we have 20K in parallel, 20K, 2 resistors in parallel that are the same resistance are just half of it. So we're going to have 10K ohms for our R Thevenin. So now we can also use what we have here to find our V Thevenin. We can use this to find our V Thevenin, is because this is something that we've already kind of taken a look at. And let's toss this plus 5 volts here to find our V Thevenin. It's a voltage divider. If you can't see that, I'll try something out real quick. So I'm gonna toss what this is really looking like, put it in simple terms of if you pulled up a WikiHow on voltage dividers, this is what it's gonna look like. But I'm adding our numbers in there, so we'll have 20K, and then we'll have 20K here. And then that'll be going to V out. or V. That's a voltage divider over the 20K. So our V Thevenin is going to be that 5 volts, and then we have 20 kilo ohms over 20 plus 20 kilo ohms, 40 kilo ohms, which is half. So our V Thevenin is going to be 2.5 volts. Awesome. Finding I Thevenin is really easy because we have, using Ohm's law, we have 2 out of 3. Let's just solve for the last one. So ITH, excuse me, we have ITH, we have positive, negative, and we have our 2.5 volts. Go out here, we have our, we got to keep that diode in here. So then we're going to have our R Thevenin for 10K. We have our diode, and then we drag this to ground. And then we have our load resistor, 20K. The 2.5 volts, what is this going to be? That's going to be in forward bias. So the forward bias is going to act like a short, and then we have V. And V is taking over that 20K. But we want to know I, and I that's going out to V out. So we have our I is going to be 2.5 volts. I equals V over R. We have our 2.5 volts over the 2 resistances there, 10K and 20K. It's good. So we have 30 kilo ohms, which would give us about 0.083 amps, milliamps. So we have our ITH, or our I, our VTH, and our RTH. And from there, we can find our V out. And our V out is just going to be this current I over our load, or times our load, sorry. Well, going through the load. So we have our V out is going to be our 20 kilo ohms, the resistor we have right here. And then we have the current I, which is 0.083 milliamps, which gives us a total V out for this question of being 1.67 volts. So now we can go on to the next part of 4.8, which this one is very similar, very much the same thing, but we do have 2 voltage sources now. So we have a plus 5 volts here. We have a 10K, or a 20K, my bad. We have 20 kilo ohms. We have a 20 kilo ohms. This is going to ground. We have a diode. Cathode, anode. Sorry, anode, cathode. We have I. And then we have a load, 20K, 10K. Oh, I got mixed up looking at the other one. Sorry. This diode is going this way. And then we have, there we go, cathode, anode, left to right. Then we have our 10K. That's going to ground. And then we have a 10K here going to a positive 3 volts. Great. We're going to do the same thing here. I'm going to start with finding R Thevenin. Actually, I'm going to bring this over to the next page just to help with space and not getting confused with numbers. Oh, RTH, R Thevenin. I'm going to draw this out differently. I got the 20K and the 20K, and the 10K and the 10K. Remember that the diode will make that. And then we got, these are going to become closed. They're going to be shorted out, the 3 and the 5 volts. And then we have the 20K and 20K. So what we'll get there, and this looks a little odd, but it'll be easy to solve. And this is how I wrote it, just to see it visually better. To go out, we have the diode here. This is going to be our diode. We have here, I'm going to move this down here. And we have, draw the same exact thing. You could probably finish drawing it. On the left side, we're going to have our 20K, 20K, and we have 10K ohm, 10K ohm. So we're going to have what's on this left side plus what's on this right side. So what's on the left side? We have two 20 kilo ohm resistors and they're in parallel. And then we have two 10 kilo ohm resistors and they're in parallel. So we have two resistors that are in parallel that are the same value will just equal half of whatever that value is. So I don't like how that looked. So then we have 20K in parallel with 20K plus 10K in parallel with 10K. 20K two 20K resistors in parallel is equal to 10 kilo ohms, and then two 10 kilo ohms resistors in parallel is equal to 5 kilo ohms. So we have 15 kilo. We have R Thevenin equals 15 kilo. Great, good. We got our Thevenin, and then we can just do we can incorporate that voltage source back in, and we can solve the voltage on this side, and then let's solve the voltage on this side. We'll do those separately. So solving the voltage on the left side is we have that 5 volts up here going on the resistor, and then we have this, and then that goes down on the resistor. That goes across. I'm going to write that as what we've already seen it as a voltage divider. So we have a plus minus, we have our 5 volts. This goes to ground. We have that top 20K ohm resistor. And then we have that bottom 20 kilo ohm resistor, which becomes our load here. And then we have our VL1. We'll do VTH1 because we're going to have to do this on both sides. So our VTH1 is 5 volts, and then we have 20K over 40K, which is 2.5 volts. And then we'll just do the same thing on the left side. We could flip it around. Now we have our let's do VTH2. This goes out. We have 10K here. And we have 10K at the top. $10K, do the same exact thing. So VTH2 is going to be 3 volts times 10K over 20K. Equals 1.5 volts. So now we have VTH1 equals 2.5 volts, and VTH2 equals 1.5 volts. So our total V Thevenin, looking back at, we have the right side and then the left side, we're going to have our total V Thevenin is going to be VTH1 minus VTH2, which is going to be 1 volt. So that's our V Thevenin. And then now we want the voltage that's going across the original diode. We want the voltage across the diode here. So when we're doing the voltage across the diode, we have our VTH, which we know is 1 volt, and then we have our RTH, which we know, what do we solve RTH for, is 15 kilo ohms. I'm going to draw that out. There are 1 volt. And now how I'm drawing this, it kind of looks like a voltage divider, right? But it's not, because that diode doesn't act as a resistor. It acts as a voltage source. And if it's acting as a voltage source and we have 1 volt here, and then what do we want? This, we're trying to what that is. This is reverse polarity. The positive is on this side, positive is on this side. So that means that the voltage across the diode is just flipped from V Thevenin. That means the voltage across this diode, so V across the diode equals -1 volt. This means that since that -1 volt, the diode, that -1 volt, the cathode here is going to be at a higher potential than the anode. And since this is in this way, it'll be at a higher potential here. This is going to be reverse biased, so it's going to be open there. So really, too, this means that the current, so I across the diode, think about it while I write it, is going to be 0 amps, because this is reverse bias. The diode wouldn't be there. There's no current. It's open. So you can and you will have a voltage, right? We know that's -1 volt, but it's open, so there's no current. So that's what would happen for this answer. This is different, interesting, kind of a tricky little thing going on. So now I'll go to 4.28. I can continue down on this line. So 4.28 question. See, and this one looks very similar to what we saw for K on 4.4. So we have this up there. We have a 1 milliamp. And then we'll go down. Diode. We'll name this D2. And then we'll name this one D1. This one, D1 though, has a resistor that goes to ground, and then we have our V, which will take over the resistor, and the resistor R. The question here, though, is we're trying to find what R has to be given that V equals 50 millivolts. So now this is interesting. This adds a little bit more. We'll name this D1. We'll do the positive, negative, and we'll do positive, negative. Makes it a little more interesting. The first thing I'm going to add here, though, is currents. I want to know the directions of currents going, so I'm going to draw those in. So there's going to be a current coming down D2 if it is in forward bias. We'd have I'll name that I2, and we're going to have a current getting split. So 1 milliamp, that 1 milliamp there is going to split, go like down, and then it's going to go. So this will be I1. Looking at that, that's a good start. That's a good setup. The first thing I would start with is maybe just writing some equations. So then writing out those equations, the easiest place to start with that. Easiest place to start with that would be by Kirchhoff's laws. So we'd have Kirchhoff voltage law and Kirchhoff current law. So we have let's do Kirchhoff voltage law and just run an equation for voltages there. So we'd have a voltage from D2. So let's do VD2 because, like I said, those diodes are acting as voltage sources. And then we have plus a VD1 plus V, right? Because these be the same, equals 0. Can you see how that's going? Because we got the positive here to negative. That's how you would put batteries like in a flashlight. You have negative to positive to negative to positive, like right. That's how you'd go out with it. So right here, we could even solve for V. So we know what V is. Ideally, is VD2 minus VD1. And then let's do Kirchhoff current law. In Kirchhoff's current law, we have that I1 and I2 split, and that means I2 plus I1, the sum, the sum there has to equal 1 milliamp. That's awesome. That's a good fact. That's something we want to know, because what we want to do is we want to find now I1, because that's the current that's going down here. That's what the resistor's worried about, and that's how we're going to find that, because we know the voltage. So if we could find the current there, once we know 2 of those, we can find the third. So we want to find I1. Finding I1, we'll just use the equation. We know the I'm out of space. Let's find I1. We know the equation for that, and that's going to use the IS, right? The IS, I know you've seen it. So we have the IS E to the VD1 over VT. Right. We're going to assume here the VT is 25 millivolts. That'll come up in the next question, like when does VT not equal 25 millivolts? But we also know what I2 is ISE to the VD2 over VT. And we can use these two together to solve. To solve for that I want. So we'll equate them, but put them over each other. So we have I2 over I1 equals ISE VD1 over VT, and then that's over ISE VD2 over VT. This is now just going to be algebra, so I might go through that. So the IS1s are going to cancel, and then we have E to the VD1 over VT. All right, over here we have I2 over I1 equals E VD1 over VT over E VD2 over VT. Remember, I'll write it off to the side before I just go into it. If we had E to the 2 over E to the 4, we actually have E to the 2 minus 4, right? So we're going to do that here. We're going to do that with this. But I'm going to simplify it a little bit more. So we have I2 over I1 equals E VD1 over VT minus VD2 over VT, which is just VD1 minus VD2 over VT. We know what VT is, 25 millivolts, right? But we also know what V is. Well, sorry. And what V is equal to D2 minus, VD2 minus VD1. So that means we could just put V in for that. So we have I2 over I1 is actually E to the V over VT. Then we could do, how do you get rid of E? Use natural log. Then we'll have natural log of I2 over I1 is equal to V over VT, which means V is equal to VT natural log I2 over I1. And now we can plug in values. We have 50 millivolts is equal to 25 millivolts. Natural log I2 over I1. 50 millivolts over 25 millivolts is equal to 2. So then we'd have 2. Let's do e to the 2 to get rid of the natural log equals I2 over I1. Well, e to the 2 is e squared is a constant. And we know what I2 equals, so we can do I1 equals I2 over e squared. And we know that I2 is equal to, looking back, I2 is equal to 1 milliamp minus I1. So we'll put that into here. I1 equals 1 milliamp minus I1 over E squared. I'll let you do that. You can do a little bit there if you want. So E squared is 7.389. So we can multiply that. 7.389 I1 equals 1 milliamp minus I1. So we can add I1 over. So we get 8.389 I1 equals 1 milliamp. And then I1 equals 1 milliamp over 8.389, which would give us 0.119 milliamps for I1. And then from there, we can just use Ohm's law. We know this current I1 now. So we know that current I1 now. So I1 over R, or I1, sorry, over, I keep saying it. I1 times R is going to equal V, but we want R. So R is equal to V over I, or V over I1 in this case. So R is V over I1, which is 50 millivolts over I1 is 0.119 milliamps, which is approximately 420 ohms. And that's how I'd solve for that. Great, and now I think we can move on to the last question, which is 4.29. 4.29, we have diode. Pull it up. So we have a diode fed with a constant current, I equals 1 milliamp. And it has a voltage V equals 690 millivolts at, and then this is at 20 degrees Celsius. So 20 degrees Celsius is usually what we're going to operate in, and that would have us at around 25.3 millivolts for our VT, or thermal voltage. So that 20 degrees Celsius is normal. But when we're looking at further in the problem, what's it like when it's negative 20 and 85 degrees Celsius? That's interesting. Like, we want to know what changes. And that's pretty easy to figure out because diode voltage, I'll write this so you can see it. Diode voltage decreases by about 2 millivolts per every 1 degree Celsius change in temperature. So this is important because in this part right now, we don't really need to know that 1 milliamp part. We need to know the 690 millivolts. So with the 690 millivolts, the first change is we're at 20 degrees Celsius. At 20 degrees Celsius, it's 690 millivolts. So at negative 20 degrees Celsius, so 20 degrees Celsius plus absolute value, negative 20 degrees Celsius, that's a total change of 40 degrees Celsius. But diode voltage decreases every one. I wrote this wrong. It decreases by approximately 2 millivolts per every 1 degree Celsius. Not change in temperature. It would be main word here is increase in temperature. So what happened here is we decreased by 40 degrees Celsius. So the exact opposite of this is going to happen. So we were at 690 millivolts, and then we decreased 40 degrees Celsius, which means it's going to increase by 80 millivolts. You see that? So we decreased by 40 degrees Celsius, which means that every degree Celsius we went down 1 degree Celsius, we increased by 2 millivolts. So we dropped 40 degrees Celsius, which means we increased by 80 millivolts. So that 690 is now going to become 770 millivolts at negative 20 degrees Celsius. And then we just do the same thing with 85, but 85 this time was a change of 20 to 85 is an increase in 65 degrees Celsius. So that increase in 65 degrees Celsius is 60 millivolts plus 65 times 2, 130. We're going to increase, we're not going to increase, we're going to decrease by 130 millivolts because we increase temperature. They're inversely proportional, which means we're going to end up with 560 millivolts at 85 degrees Celsius. Great, so now we'll move on to the second part of this question. The last part of this question is, what if the diode was in current, so I equals 1 milliamp, what if we went from 1 milliamp to 5 milliamps? So what would that impact have? So that impact will change an equation that we already have, or we already know, is our VT equal to KT over Q. K, we know, is equal to 1.38 times 10 to the negative 23 joules per Kelvin. And then we have our Q, Planck's constant, 1.6 times 10 to the negative 19 coulombs. And then T. T is going to be our temperature in Kelvin. So our temperature in Kelvin too, for just a little, you don't remember, K equals 273 273, let's just do 273 plus our Celsius value. So if it's negative 20, then we're at 253. So you can put those in, that'll be just a little extra computation just in your calculator. But we'll have our VT at 20 degrees Celsius is 25.3 millivolts, which we said earlier, and that's why we usually use 25 millivolts. That's why we assume that. We have our VT at negative 20 degrees Celsius is 21.8 millivolts, and our VT at 85 degrees Celsius is 30.9 millivolts. Great, we know that. And now we can jump back and jump to our last equation. Is we have our change in VD is equal to 2.3 times our VT, what we just solved for, and then our log, and it's our change. So 5 over 1, which would just be 5. That's our change. So our change in VD at 20 degrees Celsius with a new current of 5 milliamps, is equal to 40.6 millivolts. Our change in VD at negative 20 degrees Celsius is equal to 35 millivolts. And our change in VD at 85 degrees Celsius is equal to 49.6 millivolts. Looking at that, just a quick, we'd have 2.3 times, we defined at 20 degrees, it's 25.3 millivolts, and then that would be times log of 5. And this would be the same for all of these, except that 25.3 would change to a 21.8, and then the same here with a 30.9 for 85 degrees Celsius. So that would be the answer. That's what would change there if that current was increased. So hopefully that was good for everyone. Hopefully you got some out of that. If there's any questions, you have my email. Send me something, send a comment. I have office hours from 5 to 6 p.m. on Wednesdays. And then I'll be doing another one of these sessions here in a few weeks. So thank you. Have a nice day.